Hello, this is section 7.1 for Calc AB, and today's lesson 7.1 is just a review. The reason this section exists is because a lot of students will take Calc 1 in college and usually ends around chapter 6, and then they will pick up Calc 2 second semester. Well, a lot of times students need a refresher on antiderivatives, and that's what this section's for. So it's perfect to give us a chance to just review and extra practice. And yeah, and there are some interesting problems in this section that I want to make sure we talk about. So this whole first page, I put the basic integration rules over here on the right. I just stole that right out of your book. And then just put some extra practice problems, just ones that students sometimes struggle with a little bit, identifying if you need your inverse trig functions, using substitution and being careful with if you've got a number that you have to manipulate. In this case, it was just a negative sign. So watching out for that. Here's another substitution problem, but this is one where it's a little bit more challenging, identifying what is actually the inside and what's on the outside. So in this case, it's the exponent that you want to make your u. And then when you go to find your du, I didn't put the dx there, but usually I put a dx here. Then you look, do I have a 3 sine of x dx? Well, almost. I have the sine of x dx, but I need the 3, so putting the 3 and the 1/3 in front. But then when you go to rewrite this integral, you have an e to the u du with a 1/3, but now that's one of your basic antiderivatives that you can do the antiderivative of. So it's all about rewriting the integral in terms of u so that you can actually do the antiderivative. Okay. All right, and then this one down here below is another one that, in this case, so if you were to do substitution, because that would hopefully be your first initial response, or thought, would be to set that denominator equal to u, and then when you go to do du, you can only get 2x dx. And then here's where you encounter your problem. Uh-oh, I don't have a 2x in the numerator, and there's no way I'm going to be able to manipulate 2x to become x minus 7. So you're going to have to kind of think outside the box. Well, I could easily take this fraction and break it up into 2. So I distribute that denominator to the 2 terms in the numerator. So x over x squared plus 16 is the first integral. And then negative 7 over x squared plus 16 becomes the second integral. So now this substitution I can use with this first integral by just putting a 2 in front, 1/2, and I'm in business. So this I'm using for this first integral. And then when I look at the next one, it's telling me I have 2 perfect squares being added together in the denominator. That's arctangent. Okay, so that's where I came over here. Now I switched to w's just so we wouldn't get it confused, but I made w the x, because that would be the x squared there. And dw becomes dx, a being 4 squared is 16, and then the 7, I just moved that out in front. That's just a number, a scalar. But now I can rewrite this in terms of w. So notice my bounds. This is now in terms of u, so I had to plug 0 in to get the new lower bound, and I plugged 4 in here to get the new upper bound. And then for the w, when you plug 0 in, they actually stay the same. See how when you plug 0 in you get 0, when you plug 4 in you get 4. So don't think that I forgot. I did make sure that those bounds were correct in terms of w. They just happen to be the same. So now this antiderivative becomes natural log of the absolute value of the base. And then this one becomes arctangent. So remember, it's 1 over a, arctangent of w over a. And then you'll have to use your fundamental theorem of calculus for both of those. So plug 32 in and 16, subtract. Same thing over here, 4 and 0 and subtract, and there's your answer. So you'll notice you were able to do this, but you had to think a little outside of the box to get it going at the beginning. So just a little more fun, interesting problems in this section. Okay, so here's another one. In this case, it's definitely an arcsecant problem. You've got your 1 over x times the square root of x to the 4th minus 4. Okay, so you make your u has to be x squared. Your du becomes 2x dx, and then a, of course, is 2. But here's where we run into an issue. First of all, do you have the 2x dx that we need in the numerator? And the answer is no. Now, normally that would be a huge red flag, but because there's already an x in the denominator outside of that square root, you're already starting with a restricted domain. X cannot be 0. So normally that's the reason why we can't just introduce x into a problem, is because you have that danger of it being 0. But if we already know it's a restricted domain, we can actually multiply by 2x in the numerator, but then we have to divide by 2x. But that's perfect because that gives us the x squared we needed to be able to use arcsecant. Because remember, we have to have u on the outside and u squared on the inside here, u squared minus a squared. So it worked out beautifully. And I know that's a little bit of a weird problem. So now we've got this 1/2 in front. That 2x dx turns into the du, and you have 1 over u times the square root of u squared minus 4, which is perfect for arcsecant. Okay, so that was, again, just an interesting, fun little problem. All right, and then this one's another fun one. So the integral of 6 over e to the x plus 6. So at first glance, you stare at it and you're like, well, it can't be a substitution, because if you set the denominator equal to 0, you get e to the x, and you don't have an e to the x in the numerator. Okay, so you rule that one out. Ooh, it's really looking like an arctangent problem. Okay, so I could make it e to the 1/2 x, but then that derivative, I don't have that in the numerator. And you need to think a couple steps ahead, and that's not working either. Okay, so there's actually a really clever way of doing this. Going back to the substitution, when you set the entire denominator equal to u, the derivative is e to the x. Well, I'm close. What if I basically add 0? Add 1, then subtract the same thing in that numerator. Then if I'm clever about this, how I break up that fraction, so common denominator, make that under the 6 plus e to the x minus, and then that e to the x over the same denominator. That is perfectly legal. You could easily combine these back together to get back what you started with. But now my substitution will work with both of these. Okay. Oh, and this one actually, never mind. This one actually simplifies to 1, and then this is the one you'd use your substitution on. So just fun little problems. Ooh, this one uses your double angle formulas. So sine squared can be rewritten as 1 minus cosine of 2x, 2. And then when you distribute that 2, then you can use just a basic. Now, I know this 1/2 turns into 1/2 x. This one I use that linear trick on that I kind of hinted at in the last video. Whenever it's a linear equation that you use substitution for, you can actually, if you're getting good at these, you can skip the substitution step and just do the antiderivative, cosine, which is sine of 2x, and then you just have to remember to divide by that slope. And that saves you a step of doing substitution. Just a little shortcut. All right, this is one that eludes students sometimes because they're so used to setting the denominator equal to u, but it's actually natural log of x that you'll want to set equal to u because the derivative is 1 over x, and that's what you have. You have 1 over x dx on the outside. So moving that 2/3 in front, you now have u squared, and then that 1 over x dx becomes the du. So that's another fun little problem that sometimes will trip students up. Okay, so as you can see, just more practice, maybe a little bit harder, which is good. Give you a good challenge, help you refresh and get some more practice in. And if you need help, please let me know. Please do your homework, okay?